Welcome, and thanks for taking a few minutes out of your day to join us. My name's Todd Harris, and I lead marketing at Otigos. And today we have a couple presenters that are joining us for this live stream. We have Mike Dame and we have Ron Federman with us. Mike's a senior software engineer at Otigos, and Ron is our eBPF tech lead.
I'm Mike Dame. I'm a software engineer here at Otigos. I've been a Kubernetes maintainer. I'm an OpenTelemetry maintainer now with Ron, working on the eBPF instrumentation at Otigos a little over a year. Really excited about this stuff. It's got a lot of my background with Kubernetes and OpenTelemetry, and seeing it come together has been pretty cool. So happy to be here.
Awesome. Ron.
I'm Ron Federman. I'm an eBPF tech lead here at Otigos. Been in the company for around 2.5 years. Mainly interested in working on low-level stuff related to eBPF. I'm also a maintainer in OpenTelemetry in the Go instrumentation project.
All right, guys, the theme that we have here for this is around outages. We hear a lot about outages. It's apps and services across your environment that often take the front and center limelight, right? But that's not always the case. Sometimes it's, things like, instability inside the control plane itself, which is a topic today. And this happens to be one of those things that tracing is really good at. And it really gives us the visibility that is needed to find these things before they become trouble. If you're not yet familiar with Otigos, I'm going to do a very quick briefing for you on Otigos. Our position is that we eliminate outage risk by closing observability coverage gaps where they begin. And this provides full visibility across every service with zero code changes. And we talk a lot about zero code changes by the nature of how we use eBPF. And Mike and Ron are going to deep dive into tracing the Kubernetes control plane itself and how eBPF moves trace collection out of process entirely, which enables a lot of the magic that gives us our capabilities as a solution in this space. So yeah, that's it. Let's go. Mike and Ron, it's all yours.
Cool. Thanks, Todd. So yeah, like Todd was saying, we do a lot of distributed tracing. We talk about tracing a lot here at Otigos, obviously. The main context that we're usually discussing it, though, is in the context of the user applications of my app. I've built this application and I have these microservices and I want to trace the request as it flows through them. And a big part of that is because Kubernetes itself kind of fundamentally shifted how we think about modern application architecture. We really shifted from monoliths being the norm and having these big single applications into breaking it into isolated containers, pods, different namespaces, and breaking that all apart. So Kubernetes brought a lot of benefits in that shift too. You have things like failure isolation, separation of concerns, but it also brought with it some new problems, not worse or better problems, but just different things to think about when we're dealing with apps. You've got that failure isolation, but you still need to know how that isolation, if it's not totally isolated, how that affects your application downstream, or if you're seeing a failure, is that coming from somewhere else in the pipeline? Because even though your microservices are now operating as discrete parts, they're still functioning together as that whole application. And so you need to really treat it holistically as this is one thing, even though it's split up a lot. And yeah, so that's kind of where traditional signals like logs and metrics started to fall a little bit short of just seeing the whole picture. Not that logs and metrics are bad, they're still extremely valuable, but the overall shift is what led to tracing kind of emerging as a necessary signal in these modern applications, so that you can still see that holistic view. So this is what's really been driving the idea of stitching together microservices and seeing that whole request flow in your user applications. But we still don't really hear much about tracing the platform itself or the control plane. And you kind of have to wonder sort of why is that? But first off, what are we talking about when we say the control plane? What do we mean by that? This is what we're referring to. You're probably very familiar with some of these components, if not all of them, but just kind of as a quick brief overview. Things like the API server that's handling every API request in the cluster, a controller manager reconciling your deployments, making sure the number of replicas that you need are up, things like that, services, endpoints. The scheduler, a lot of people are familiar with that. Why are your pods going onto certain nodes? What nodes are being chosen? And then at the core of it, you got the kubelet orchestrating everything, and obviously the container runtime. And so you can kind of see from this diagram here that Kubernetes itself is also microservices. The platform itself is microservices, but this isn't just a layer that's existing below your app. It's something that your app is using all the time. It's part of your app. It's an extension of your application. Even if you're not directly making API server calls or calling Kubernetes resources, your app can't exist without these things functioning properly. It's just not going to work on Kubernetes. So if the Kubernetes platform is an extension of your application, you should treat it like part of your application. It's the full end-to-end, as we're talking about. This holistic view it includes Kubernetes too. If you're building on Kubernetes, you're building for Kubernetes. So in that sense, we should be looking at tracing the platform itself too, because that is tracing our application. So what is the state of tracing in Kubernetes? This is kind of what we're talking about here. Is what we're going to show today is not just generic eBPF. Some people talk about eBPF tracing as being just network traces or service maps or black box input output that doesn't really give you the whole picture. These are manual spans that have been added to the control plane components by Kubernetes maintainers. And they've been added for a long time. This has been started since around 2018. This was the first KEP that I'm familiar with that has OTel spans being added to the API server. In 2018 was actually before OpenTelemetry was even a thing. I think it was just we're looking at open tracing spans at the time. So the API server has these spans put in. The kubelet has similar spans. The scheduler has spans being proposed now. Things like etcd, cryo, containerd, all of these core components that can be really nested deep down into your application and kind of invisible to you most of the time, do have this tracing that's available. And this is an example, this screenshot is an example of one of those traces to kind of show you that it's more than just like HTTP calls. It's something that the developers and the maintainers thought would be important. You're not going to get information like this, like the webhook name, the resource, the sub-resource, by just generically tracing the platform itself. You want to activate these spans that have been put there for a reason. But still, there's a lot of people that, even though some of this has moved to GA, it's available and it can be on by default, it's not used by a lot of people. It's not activated by a lot of people. But a question that a lot of people do have is why should I activate this? What benefit am I going to get out of turning on these spans, and why do I need to trace the platform? And it's a really good question. What it ultimately comes down to is that a lot of times, or at least sometimes, your app is really the victim of what's causing the outage, and it's not the cause itself. We have an example here from OpenAI, pretty notable example from, I think maybe a couple of years ago, where they had an actual telemetry service was overwhelming the Kubernetes control plane and causing them to have an outage. And so that doesn't show as your application tracing. If you're just tracing your application, you're not going to see that whole picture. But there's a laundry list of other reasons that could be why you want to trace the control plane itself. Things like, why are my nodes so busy? Why are so many resources being consumed? Why do my pods take so long to start? A big one here is scheduling. So I worked a lot on the scheduler when I was maintaining Kubernetes, and most people really think of the scheduler as, I'm just balancing resources, or I've got node affinity, pod affinity. But the reality is that by default, the scheduler runs with over 20 different algorithms out of the box that most people don't ever realize or tune at all. And those are all impacting the scheduling decisions. And you don't see them. The logs are not very clear about what it's doing. And so part of my first experience with OTel was trying to add some traces to the scheduler to get some of that visibility. And we actually were able to fix some bugs in the scheduler itself, but it also answered a lot of questions that people had of, well, my pod is showing up on the wrong node. Is this a scheduling bug? What am I doing wrong? I'm setting an affinity, but for some reason it's getting pulled and scored to a different node. This is where that deeper platform visibility can help you run your application a lot better. The key takeaway here is that application tracing is really only going to start after your pod is running. So things like scheduling, admission webhooks, long container pulls, those sort of things aren't going to show up if you only do trace.start within your application. Issues with controllers that trigger requests from other controllers. Your pod creates a CRD that gets reacted to by another controller. That sort of pathway isn't always totally clear unless you're seeing the flow go down to the control plane itself and then back out. So these are just some of the reasons, but it's really an open-ended question, and there are a lot of things that you might not even realize are things that could be shown from tracing. It's kind of like asking, what would I do on Kubernetes just to run? I'm asking, how would I debug it, is just as much of an open-ended question. And so we put a lot of things on this slide. There are a lot more reasons that I'm sure anyone that's worked with Kubernetes can sit down for a couple minutes and come up with some of their own issues that are similar to this that would have been helpful to be able to trace a request or an actual flow through the control plane. But if this is also obvious, like, what are some of the drawbacks? Why aren't people activating this by themselves all the time? And it really comes down to a lot of the main drawbacks to this control plane tracing are some of the main drawbacks to normal manual instrumentation in your application. The problem that we're solving with OTigos for user applications extends to that same problem with the control plane. And it even becomes a little bit worse. You have overhead of manual instrumentation using memory and resources to do that tracing in your application. Imagine that in the API server, especially if you're already trying to debug some sort of outage or resource pressure. You don't want to have your observability impact what it is that you're observing. So that's one reason, that's one pushback in a lot of the KEPs that I showed of why even add this in the first place. Then there's the config itself. Just like adding manual instrumentation takes developer cycles and takes tuning and sampling, you have to do the same sort of config to turn on these spans in the control plane. It's even made a little bit worse because, as we'll talk about, a lot of the control plane pods aren't normal pods, they're static pods, so they're effectively just processes running on the host. So to configure that tracing, Kubernetes will usually expose some sort of config file, like this example here in the API server, where you can turn on tracing, but you need to be able to put this config file onto the host itself and update the API server, restart that pod with an argument with a path to that config file. This isn't just like a CRD that you can create in the cluster. This is something that you need host level access to be able to mount. And then another problem, same as with your user applications, if you're going to turn on tracing, you need to restart the application. You need to restart the API server. If you're already in an outage, you don't know if the API server will even come back up, and now you're even in a worse position. So that's a lot of the drawbacks are I'm kind of trying to show the parallels between the control plane tracing and user application tracing. Just like it's an extension of your application, the observability is an extension of your application observability. So with a lot of those problems, just in general, what we're doing at OTigos for user applications is to try to operationalize that and make it a lot easier to approach. Reduce that overhead, obviously using eBPF, but also reduce the config and the restarts that are necessary by making it a lot easier, separating the team concerns. So everything being CRD and operator based in our control plane, our observability manager means that you don't have to touch the applications at all. eBPF itself doesn't have to touch the applications, but the entire management and config can be separated. And we do this with an operator-based control plane. It's all CRDs to define what you want to instrument, where do you want to send that, how do you want to process it and mark it up. And that same solution that we worked on is then also applies to how we're going to show we instrumented the control plane here too, pretty easily with a couple different changes. But digging a little bit more into that, this is how the OTigos control plane runs. This is an example of our application. It's kind of simplified a little bit, but just to show what we have a couple different operators that are communicating with each other. We have our core component, the OTiglit. We have an instrumenter that tells the OTiglit what to instrument, what eBPF programs to run. We have our collector pipeline managed by something called the autoscaler. We deploy a collector. This shows the custom resources that configure all of that. And actually a similar issue that we were trying to debug recently for a user was, so you can see this UI pod here creates a CRD that then goes to the autoscaler. And so there was an issue with the CRD getting passed through a webhook, and it was unable to call the webhook for some reason. We couldn't figure that out. And if you already know the control plane a little better than apparently I did, you might start to see what the issue was here. But the main reason was what it ended up coming down to. We found that the user had a network policy in the namespace that prevented cross namespace traffic. And that was kind of surprising, at least to me. I don't know, maybe more people know it better, but I think it would be a good trivia question is that even though the UI was talking to the autoscaler in the same namespace, that webhook was seen as cross namespace traffic. And the reason is because the webhook was actually being called from the API server when it handled the CRD creation. That runs in the kube system namespace, which is obviously different from the OTigos namespace. And that we were able to confirm by looking at this cluster tracing. We were able to actually see the request go from the UI to the API server, which then called the webhook, which then created the CRD in the same namespace. So even though we were kind of able to debug it and figure it out ourselves, we were able to visually confirm that, and now we know that that is the issue. So you probably have applications that look similar to this, but whether you're building for Kubernetes or whether you're building on Kubernetes, the message is still the same. You're still building an extension of Kubernetes itself. So you need to treat Kubernetes as part of what you are doing so that you can have that whole picture end to end. that's kind of a quick overview of what we're doing and why we're doing it. And now Ron's going to go a little bit more into detail on really how we did it, some of the differences between tracing the applications and tracing the control plane, and how we tied that into the OTel control plane, and give a quick demo of us. So Ron, you want to take it away?
So Mike talked about how OTel manages instrumentation and basically accepts the user inputs using CRDs. So at OTel, basically the input can be arrived from two sources. One is through the UI and one through directly applying CRDs. And the basic CRD that we are using to get user input to what we should instrument is called the source. And this is an example here on the right of what the source looks like for instrumenting the control plane. So basically what we're saying is we're going to instrument the entire kube system namespace, and the OTel will auto-detect all the relevant applications that are running in this namespace and try to instrument them. So that's like how the input is looking like. A bit more about like how the actual instrumentation is being done. So the Go Auto Instrumentation is a project that exists in OpenTelemetry for about 3 years, I think. At OTel, we have an extension of this project, which uses eBPF to instrument Go processes. And since the control plane consists of multiple applications which are all written in Go, we can use this approach to instrument them. Usually when applications are adding manual tracing into them, like Mike showed in the API server, like inside the code, they're calling like trace.start or trace.end, and that's just like calling the OpenTelemetry API. The OpenTelemetry API is basically just like an interface. It doesn't really contain the actual span creation and sending. That's what the SDK is for. The SDK is like the actual engine that creates the spans and bashes them and sends them to somewhere. So by default, like the actual spans are like getting created in the code, but because this is not like on by default, they're not getting sent to anywhere. So it's like it's there, but it doesn't really do anything. So that's where like the Auto SDK comes in. It's a feature that was added to the OpenTelemetry API roughly a year ago, and basically enables like us from the eBPF perspective to hook into the like manual spans that are being created with the OpenTelemetry API and integrate them with the eBPF spans. So it's kind of like it's kind of like looking like magic, but like the application is calling the OpenTelemetry API. It doesn't really initialize an SDK. It doesn't send the spans to anywhere. But because like this Auto SDK is like inside the OpenTelemetry API, we can integrate it with the eBPF programs.
And Ron, just to emphasize that this is something that is built in on, it's not on by default, but it is there by default. It's a direct dependency of the OpenTelemetry SDK. So anywhere that they've put these spans, or really where anyone has put spans in any of their applications for that instance, has the ability to have those spans activated by eBPF asynchronously with zero overhead. And so that's the way to think of it, is that the spans are there, and this is just kind of like, Frankenstein, like putting the electricity to them and turning them on and then handling them separately. And there's no extra dependency, no feature flag or anything that you need to import. It can identify them and attach to them automatically.
Right, exactly. Okay, so moving on, a little bit about like how the control plane is actually being run. So if you think about it, it doesn't really make sense for the control plane to be a pod or a deployment, because it's the actual thing that creates pods in deployment. So it's kind of like a cyclic dependency. So static pod is like, it looks like a pod, but it's not a pod in the usual sense. Like you can't really delete these pods from kubectl. The real source of truth of static pods is like manifest files that exist on each node, which define like what is the API server manifest is, or what the etcd manifest is, or all the other control plane components. And because these are like defined by files on the host, they are not like restartable like in the sense of usual pods in Kubernetes. So usually when you look on like observability tools in Kubernetes, the usual approach, and we also do it in OTel for other languages, but it's basically like you need to add some environment variable, or you need to add some mount to your pod, or like a sidecar or init container, some manifest change in order to enable the instrumentation. But this approach is not really doable with static pods, because you can't really change them like in the sense of regular pods during runtime. So like the only way to instrument them is something without a restart, which is eBPF. Okay, so now I'm going to share my screen and do a little demo. What I have here is a small client cluster, and I already have Odigos installed, and I created 3 source CRDs to start. So the source CRD is what actually tells Odigos what to instrument, and currently we have 3 sources. One of them is the control plane source that we showed. Basically, it just looks like this. It tells it to instrument the entire kube system namespace. And the 2 others are actually Odigos themselves. So I want to get spans and traces also from the Odigos instrumentor and the Odigos UI. And you can see that these are like not namespace sources, these are deployment sources. So specifically to the Odigos instrumentor deployment and the Odigos UI deployment, both of these are also instrumented. So that's what I have in the class, like in sources aspect. I also want to show you, I have here a simple application in the simple demo namespace. Basically a few microservices that simulate like a usual like a store kind of operation, content and inventory services, etc. And there's also like a load generator cron job that runs every minute, and it just do like a few queries to the front end and stop. So it runs on every minute and it stops. So currently this namespace is not instrumented by Odigos. Like right now what we have in the cluster is only the 3 sources that I showed, like these ones. So I want to show you. So I already configured Odigos to be connected to Jaeger. I have a local Jaeger instance running. And what you can see here is like very typical to like this cron job pattern. You can see it's like every minute we have a trace, selected traces on the control plane, which calls a webhook. So if we open one of these traces, you can see that this trace, for example, it starts from the controller manager. The controller manager is the entity that actually manages or creates the cron jobs. So controller manager is actually the one that's implementing the schedule of the cron job. So on each minute, it will try to create a pod. And this is the exact workflow that we see here. So it starts from a post from the controller manager, and it goes to the API server. The API server will try to create a pod. It will go to etcd, and we can see this entire flow here. A few interesting things to note here. One is that we can roughly classify the spans here to 2 categories. One is like manual spans from inside the component, like this list operation. This is like the spans that are inside the API server. And the others are like this post. This is like the automatic HTTP, eBPF collected spans. So we can see here both of these types. And also down here, we can see this call mutating webhook. This is like the manual span inside the API server. This actually does an HTTP client request, which goes to the Odigos instrumentor, which has a webhook. So this is like the cross namespace communication that Mike mentioned earlier. We can see it here. It goes from the call mutating webhook into the HTTP client and then to the Odigos instrumentor, which serves this endpoint. So the last thing I want to show is actually instrumenting this simple demo application. So I'm going here to the Odigos UI. I'm going to instrument the simple demo namespace, give it a few seconds. And again, remember that Odigos UI is also instrumented. So we're going to see what it actually do here. Now let's refresh this, and this is the actual Odigos UI trace. So it starts from the Odigos UI. It has a GraphQL endpoint. Basically, when I click this button in the UI, it goes and creates 6 sources. And this is what we can see here. So Odigos UI is trying to create those 6 sources CRD because there are 6 applications in the namespace, simple demo. And you can see each of these tries right here. Like it's, yeah, there it is. It does a post of this source. This is like the geolocation source. It does a post, and then it goes to the API server, and the API server has both a mutating and a validating webhook. So let's see this one. It calls a validating webhook, and then this is the HTTP client request, and the Odigos instrumentor is the one that serves the actual endpoint. So that's basically it. We're seeing here like both the HTTP level spans and the manual spans from within the control plane and how it all interacts with Odigos. Yeah, so that's basically it.
Yeah, and
Beautiful.
I also wanted to point out that even though I talked a lot about how this isn't just eBPF spans, the big point is that these link to eBPF spans. So a lot of the gold is the manual spans that the maintainers have added. That's the tough stuff to get to and activate, and that's got a lot of really good information that they decided to manually add. But it also links to that stuff that we're adding through outages with eBPF to your applications, and even getting things that the maintainers aren't tracking themselves, like the post requests or the eventual user space application requests. So awesome demo around it. It's a great full end-to-end view of what we're doing here. And a lot of it is based on open source, but then we, of course, add a lot more through our platform too.
So you guys all see a QR code on your screen right now. What you saw from Ron was a little taste of what we could give you, thinking about your own environment, more of a walkthrough of how OTGhost would work in your environment from a tracing perspective and from a visibility perspective. And again, thinking about what we kicked this off with around the concept of outages and catching these things before they become, that domino effect happens across your, services and apps. And in this case, we're talking about the control plane. So if you scan that with your phone, you can check it out and sign up, and we'd be happy to chat with you for a few minutes to show you a little more about this and take it a little bit further beyond what Ron was going through in the time that we have now. But I think you'll enjoy it. So, hey, thank you everybody for joining. This was a quick session, but hopefully impactful for you guys. And of course, thank you to Ron and to Mike